Hi, my name is Abel Faure Beaulieu. In this video, I will briefly summarize my PhD project, which was part of the Annulight program funded by the European Commission. I will talk about combustion instabilities which occur in combustion chambers of civil jet aircraft engines and land-based gas turbines for power generation. These instabilities are a major engineering problem that slow down the development of low-emission power systems. But let's put some context first. This plot represents the global increase of the Earth temperature for different policies of mitigation of greenhouse gas emissions. This first line corresponds to a scenario without any mitigation policy. The second line corresponds to the scenario where carbon neutrality is reached by 2100. The third line corresponds to the scenario where carbon neutrality is reached by 2050. And the last line is a scenario accounting for the implementation of large-scale carbon capture, which is not yet possible. According to the IPCC, the temperature anomaly should stay below 2 degrees Celsius to avoid catastrophic consequences. This corresponds to the third scenario. Therefore, at the COP21 in Paris, 220 countries agreed to aim at carbon neutrality by 2050. A promising path towards this objective is the use of renewable energies to produce electricity. However, these energy sources have some limitations that need to be overcome. One of these limitations is the impossibility to use them for civil aircraft propulsion. Indeed, current batteries are too heavy to imagine fully electric transport aircraft. For everyday's energy consumption, another limitation of renewable energy is their intermittency. Because wind and sun fluctuate, the energy production does not match the energy need in real time. For this reason, it is necessary to develop large-scale energy storage technologies to store the energy excess and release it when necessary. Several technologies exist to store energy. One of them, which is very promising for large-scale storage, consists in using renewable electricity to extract hydrogen from the water. This hydrogen can be stored and used when necessary to produce energy. One possibility is to use it in a fuel cell, suited for marine or land-based vehicles or small-scale power plants. Another possibility is to burn it in a gas turbine, which is particularly suited for transport aircraft propulsion and large-scale energy production. But burning hydrogen in a gas turbine is a technical challenge. One of the main problems is the emergence of thermoacoustic instabilities, which are a type of combustion instabilities that I will now explain. Here you see a simplified cut of a gas turbine combustion chamber. In this chamber, the flame acts as a source of sound. The sound is reflected back towards the flame and modulates the incoming amount of air and fuel, which in return modulates the combustion noise. The loop is closed and can be unstable. An initial perturbation can grow after each cycle, leading to high amplitude acoustic pressure oscillation and large flame displacement that can damage the engine. Here you see the downstream part of a typical gas turbine. One can see the combustion chamber and the blades of the turbine. The shape of the chamber is annular in most of the cases. Let us now have a look at a typical thermoacoustic instabilities in an annular combustion chamber. The color represents the growing acoustic pressure oscillation. One sees that the acoustic pressure spatially varies around the chamber. This is an azimuthal mode, the most common in this type of chamber. The state of such azimuthal modes is classified into three different categories. The spinning modes, traveling around the chamber at the speed of the sound. The standing modes, staying at the same position. And the mixed modes, which are basically a combination of the two others. In reality, one observes that modes constantly undergo transition between these different states. To understand what causes these transitions, I developed during my PhD a physical model for thermoacoustic instabilities in annular combustion chambers. This model accounts for the nonlinear response of the flame to acoustic excitation, to the presence of turbulent combustion noise, the effect of mean flow, the presence of asymmetries of the mean temperature field, asymmetries of the acoustic properties of the chamber that could be due, for instance, to the presence of acoustic dampers, geometrical asymmetries, and discrepancies between the flames caused by flow asymmetries. Additionally, to describe the nature of the mode state, we introduce a variable chi, the nature angle. When chi is minus pi over 4, the mode spins clockwise. When chi is negative, one has a clockwise mixed mode. When chi is 0, one has a standing mode. When chi is positive, one has a counterclockwise mixed mode, and when chi is exactly pi over 4, one has a counterclockwise spinning mode. In parallel to the physical modeling, experiments were conducted on the lab-scale annular combustor of NTNU in Norway. The physical model allowed to explain and reproduce many of the phenomena observed in these experiments. As an example, here is a time trace of the nature angle chi observed in one of the experiments. It shows intermittent jumps between a positive and a negative value, respectively a counterclockwise and a clockwise mixed modes. With the model, it was shown that these intermittent transitions are caused by the turbulent combustion noise. For different operating conditions, the following time trace was recorded. This time, the nature angle undergoes periodic oscillation, corresponding to periodic inversions of the propagation direction of spinning modes. This unexpected phenomenon was shown to arise in presence of small asymmetries in the system. These two examples are only a small part of the vast range of thermoacoustic dynamics that the model can handle and explain. The experiments and the model contributed to give us a better understanding of the phenomena at play in annular chamber. This understanding will be precious for future developments of low-emission gas turbines for aircraft propulsion and power generation. And if you are interested for more details on this topic, you can have a look into the publication I wrote or contributed to during my PhD.